Um, Good day. We will now be discussing. We will now be discussing a topic for feedback and control systems, in which we would be modeling electrical circuits using differential equations. Remember from last time we mentioned that from the process of designing a control system after creating the objectives, our next step is to actually create a model of the system. Now, one of the things that we could use for modeling a system or a proposed system would be to use differential equations. So for this specific supplemental video for that course, I'll be showing you the basics of how we could model electrical circuits using differential equations. Now, although there is another way of modeling using Laplace transform, it would be easier to appreciate differential or using differential equations or using Laplace transform rather when you learn how we actually model them using differential equations. We will start with how we represent common components or electrical components as their differential equation counterparts in terms of its current and voltage. So for resistor, it's just using Ohm's law, which is VR equals IRR, or voltage equals to current times resistance. But if we are to actually, oops, that's a bit too thick. Just thin it out a bit. Okay. So if we're actually going to use current, so IR would be equal to VR over R. Okay. Next, for capacitor, capacitors are shown as the current passing through it is equal to its capacitance multiplied by the derivative of the voltage inside it with respect to time. So that would be IC equals to C dVC dt. But if we want to use voltage, so we transfer C first, so we divide both sides by C. So we'll get IC divided by C equal to dVC over dt. Okay. So we multiply both sides by dt. Okay. So we will be getting IC over C dt equal to dVC. Now if we are to get dVC, we integrate both sides. Okay. So integrating it would cancel out the derivative here. So finally our VC or voltage inside the capacitor, we take out over C as this is a constant. So 1 over C integral of IC dt. Okay. So this would be our voltage equation. Okay. Now for inductor, we already have the voltage. Okay. So what would actually look like is it would also look like this one. So if we are to represent it as, if we use the same, because they look the same, so if we use the same procedure, it should become IL over 1 over L integral of VL dt. Okay. Most of the time, we will be needing this first. Okay. So this is voltage and this one. So if we need to transform the component in terms of their voltage, we need this, this, and this. Please take note of this too, as this is not found on your handouts. If we need to represent the component as current, or let's say we were using Kirchhoff's current law or whatever, we would be using this as our current representation. Okay. Okay. Now we will be using two um, examples in order to represent, or in order for us to understand how we will be using these equations, and then use it to represent electrical circuits and their components and their variables as differential equations. Depending on what is needed, we will be doing different things or different methods. But in order for us to be able to have a grasp or a firm understanding of how we'll be using this, we will have a consistent type of question. Let me just erase this. Just make sure you understand how did this become this equation from here. So let me just get my two examples, and hopefully you could follow along. So we have our first example here, in which we are to determine we are to model I1 and I2 as differential equations using, in this case, mesh analysis. Now, once we have modeled I1 and I2 as differential equations, we could use those differential equations to be able to get the voltages or individual currents for the components. So we have a single voltage source, which is VT, an 8 ohm resistor, and a 10 ohm resistor at the far right, a capacitor with 1/16 farad value, and an inductor with 1 Henry value. So the first thing we have to do is to actually represent first. So we will be doing step 1. Okay, is we have to represent I1 and I2 loops using KVL. Okay. So technically what we're going to do is use mesh analysis, okay, to solve for I1 and I2. So for the first loop, okay, so for loop number 1, we will be using KVL as mentioned. We put all of the voltage sources on the right of the equation and all the other components on the left. So we have to represent it as voltages. Now this is where we will be using our equations here. Okay, so because we are going to use or represent this as voltages, this, and this would be important. So the first one is a resistor, and it shows that it's equal to the current times the resistance. In this case, the current passing through 8 ohms is I1. So in order to represent that using Ohm's law, we will be having current times resistance. So we'll just put in the constant first, which is the resistance, multiplied by I1. Now there's another component in the loop, which is 1 over 16 farad. And if we're going to represent this as a voltage, capacitors are shown or are represented via this. So the voltage here is equal to 1 over the capacitance integral of the current multiply current dt. So the capacitance is 1 over 16, so we'll get the reciprocal of 1 over 16, so that will be 16. Okay? So 1 divided by 1 over 16 is 16. So we'll write that. Then integral. Well, we have to represent this as a definite integral. So it would start from 0 up to where t is. Okay. In some texts, they instead of putting 0, they put in negative infinity. Okay. That's okay. So now we have the current, and we need to represent it using the current passing to the capacitor. But unlike the resistor where only I1 is passing through it, the current has two loops going through it. I1 in this direction and I2 in this direction. So if we follow the loop, it's going downward to the capacitor. If we follow this loop, it's going upwards to this capacitor. So they are actually opposite of one another. So that would be I1 minus I2. Need to write that. Now you might be asking, why not I2 minus I1? Well, we're looking at loop 1, so our main current will be I1. If we were doing it here, then it would be I2 minus I1, as you would see later. Okay. And let's not forget dt. Equal to the voltage sources. There's only a single voltage source from that loop, and that is Vt. Now, how about for loop 2? For loop 2, okay, so there's no voltage sources, so we could expect the right-hand side to be 0, but we have 3 components. Let's start with a simpler one, which is 1 Henry. If it is going to be represented as a voltage, it says here it's L DIL over dt. And because L is equal to 1, then it would just be DIL over dt. So derivative of the current passing through it with respect to time, and the current passing through it is only I2. So this would become dI2 over dt. Now, where's the 1? Well, of course, you should have already known that we don't put in the 1, and it's a constant. So it's supposed to be 1 Henry multiplied by dI2 over dt. Next, we have the voltage in the resistor. So just like the one here in loop 1, so we have 10 ohms, so 10, but it's not I1 passing through it, it's actually I2. So we write I2 here. And then finally, we also have this one again. It's the same equation as this one, as nothing changed, except that our main current in this loop is I2. So we would be reversing this. So it would be equal to 16 integral of I2 minus I1 dt equal to 0. Okay? So that would be our main two loops. Okay? So that's actually our first step to represent this as uh, loops in mesh analysis. Let's try what we've learned from the first example and apply it in the second example. So this time around, try to do it first. Okay, I'll give you time to do it first. Not really. I'll ask you to pause the video and try to represent this circuit as two individual loops, and we will be using KVL for our mesh analysis. So let me just write loop 1 and loop 2 for you first. Of course, this would be our loop 1. Don't mind this for now. So this would be our I1, and of course this would be our I2. Okay? So what I want you to do is to represent the two loops using mesh analysis, KVL, and the equivalent differential equations of the two circuits. So pause the video first, and then let's see if you have the correct answers. I'll be starting with our solution in 3, 2, 1, and let's begin. So let's have our loop 1 first. Okay. So loop 1. So we have a voltage source, so we know that it would be on the right side. So this is I1. We use our Ohm's law here. So that would be 4 I1 plus we have another one here, but this time it has I1 and I2. So this would become 6 I1 minus I2. You should know by now why this is subtraction, as they have opposite directions coming through this specific line here. And then we have an inductor here. So with the inductor, we will be having DI or L, DIL over dt. So this is 1 Henry, just like our first example. So this would just be DI1 minus I2 over dt. Okay. Well, technically we could already have this separated. Let me just do that instead. Okay. So instead of, well, that was supposed to be the proper way of doing that. So just put in DI1 over dt minus DI2 over dt. Okay. Equal to V of t. So there we have it. We have the first loop, the resistor, the two resistors, and the inductor. Now for loop 2, let's start with the capacitor. So this would be the reciprocal of 1 over 4, so that would be 4. The integral of I2 d of t from 0 to t, or again for some text, negative infinity to t, plus and we'll have this, but we'll have 6 I2 minus I1. And then we have this one as well, but the opposite. di2 d of t subtracted by di1 over dt. Again, this is the inductor. This one, the 1 Henry. It has a minus on it because there are two currents passing through it. Then we have here we have the resistor. So reverse I1 minus I2, I2 minus I1, and then we have the capacitor here for this one. Okay? So this would be our equation 2. Did you get that correctly? If you made some mistakes, you just have to correct them. Make sure not to make the same mistake again when you're solving these types of problem. Anyway, let's go to the next step of our first example. So we're done with our first step, in which we represented the loops or the mesh loops into its appropriate KVL equivalent, together with representation of each component into its derivative or voltage equivalent. Okay. So what we're going to do next is, for the second step, is to remove any instance of integrals. As we want this to be a differential equation, we want them to be removed. And the way to remove them, or to cancel out an integral, is of course to do a derivative. So we differentiate the equations until all the integrals are eliminated. So we do that first with the first loop. So we differentiate all of this in order to remove this. Okay. So what would happen? So we write first the derivative of 8i1. So it would just become 8di1. Just erase a little of here. Okay. Next, when we do a derivative of the second term, it would just cancel out 0 of t and dt. Plus, we'll now have 16 I1 minus I2. And then finally, we differentiate our last term. So we get dv of t The only thing that you should not forget is that I forgot actually, is the independent variable. So this one should have d of t here, and then this one should also have a d of t. Okay. So this would be our first equation, or equation 1. Okay, this is our second equation for loop 2. Now for loop 2, so let me just point this out. Okay. How about for the second equation? So there's an integral here, so we differentiate it to remove it. Now if there's no integral in the equation, we leave it as is. How about if both loops does not have any integral? Then we actually skip rather step 2. It's easy to know or determine if we're going to have step 2 or not. If there's a capacitor on the circuit, then definitely we'll have a step 2, as the voltage of a capacitor is shown as an integral. So let me differentiate the first one. So this is already differentiated. So we'll have the second derivative of I2, okay, over dt squared. It's the second derivative already. We differentiate this one. So we'll have 10 di2 over dt. Okay. Then the integral here, or the integration here, would be cancelled out by the derivative. So this would become 16 multiplied by I2 minus I1. And that would be equal to 0. Just to summarize, the second step involves removing the integrals by differentiation. So, by finding the derivatives of each term and then making sure that integrals are removed, you would be able to show the mesh loops as a proper equation. Let us now apply what we have learned from the first example for step number 2 in this equation. So this time around, step number 2, just to remind you guys, we will be differentiating the first and second loop to remove integrations or integrals. I'll be giving you a few minutes to try to determine and differentiate each equation if needed. Then afterwards, compare it to how I will be doing it. Go ahead and pause the video. And then do it on your notes. So 3, 2, 1, pause. Okay, let's now compare what you have on your answers and see if you were able to do the second step correctly. Now, I've already mentioned that we only do the second step if the equation has an integration. So loop 1 does not have any integrations on it, so we do not use the second step to transform loop 1. But the second loop has an integration. So we'll be doing the second step on loop 2. So this is already going to be used as is. And we'll be doing the integration on the second loop here. So we find the derivative of this one. So this will just cancel out. So what we'll have is 4I2. So the derivative or the integral has been removed. Then we have to find the derivative of this one. And because derivatives are linear, we would have 6di2 over dt minus 6di1 over dt. Next, we'll have the second derivatives of both of this. So d squared I2 over dt squared minus the square of di1 over dt squared. Okay. I forgot to put the equal 0 here, which we also need to put here. So this should not be a problem anymore. And hopefully you were able to get the correct answer for that second step. Again, we won't be needing to differentiate this as there's no integral here, but we have to do it at the second loop. Okay, so we'll now go on to the third step and use it on our first example. Let's now apply the third step to this example. Now the third step is actually optional, but it simplifies the remaining steps quite a lot. And what we'll be doing is we will be representing the derivatives as a variable so that it's easier to look at and easier to work on. So what do we mean by that? So the third step is we represent d, or we use d as a representation of the derivative d over dt. So we will be doing this for the for both loops before we go on to the fourth step. So let's work on this on the first equation. 8di1 over dt plus 16i1 minus 16i2 equal to dvt over dt. So let's move this a bit downward. Okay. So we have the, I'll try to divide the steps using this blue thing here. So this is our second step that we did a while ago. Okay. So this would now be our third step. So we replace d and dt by a big letter D. So this would become 8. Then we have d I1. Now you might be asking, where did the I1 come from? Remember that we only exchange the big letter D for d over dt. And I1 is not included in that. So I1 would be here. Okay. Then we have 16I1. Let's separate that already, as it has to be separated. I should have separated this a while ago already. And this would be 16I2. Then we also have our dvt over dt. So we replace d over dt as a big letter D times vt. Okay. So this would now be our new equation 1. We do it on the second loop as well. So this one is in squared. So this would be d squared I2 plus, so we have a d here, so 10 d I2 plus, let's separate this to 16 I2 minus 16 I1 equal to 0. Okay. So again, the third step involves replacing all d over dt by the big letter D. Now looking at the two equations, you'll see that it's easier for us to understand this than looking at this. In any case, once we're done, we're going to bring back or resubstitute d over dt for d as well. Once we have this, the subsequent steps would be a lot easier to determine, unlike if we didn't transform it into a big letter D. So this would be our third step. So this would be, let me just put the phrases here. So this is step 1. Oh, it's too tight. Oops. Yep. So this would be our step 1. This would be my second step, step 2. And this would be my third step, step 3. Okay. So we are exchanging this in our fourth to third steps. Now let us apply the third step to our second example, in which we will replace the first and second equations, the d over dt, with capital letter D. So let me just write this on our board here. So let us replace, or let d equal to d of t. I took the liberty of boxing steps 1 and steps 2 a while ago. Let me just move this a bit here. So we have the first equation here. So for I1, I don't have to change anything there. So the first equation, so we have 4 I1 plus 6 I1 minus 6 I2 plus, this is the number 2. Then we have di1 over dt, so that would be a big, oops, I'll replace this with a big letter D, I1, minus, we'll replace d over dt with a big letter D as well, and then we have I2, equal to v of t. Then we have our equation here at the bottom that we applied the second step a while ago. So no change here, so this would still be 4i2 plus, so these has a couple of d's on it, so this one will be 6d I2 minus 6d I1. Remember, I'm just replacing the d over dt with the capital letter D from this step. So this would be d squared I2. And finally, we have d squared I1. So that will be d squared I1 equal to 0. So we're done with our step number 3, in which we're trying to simplify the differential equations, or the solution for the differential equations, by letting d equal to d over dt. Now let's take a look at the fourth step and apply it to our first example. Okay, so we will now be applying our fourth step in getting the differential equations for I1 and I2. So we were able to simplify this a bit, but we're not done yet. The step 4 includes eliminating one of the variables by doing a number of methods actually. So this is a classic two equations, two unknowns. From your algebra and advanced algebra classes, you should have an idea of the different methods. So you could use substitution, elimination, you could use matrices. So there are a number of ways to do this. Okay, so let's try to fix this a bit and see what are the factors for I1 and I2 for equations 1 and 2. Let me just write in the equation number here. Okay, so this was the equation 1. What the? There we go. And this would be equation 2. Well, let me just change the color of that, as that is not really functional. Here we go. So let's have this as equation 1. And this is equation 2. So we'll try to isolate I1 from I2 and then make sure that all the other voltage sources are still on the right hand side. So for this one, we have 8 and 16 for I1. So we'll factor out I1. And that would give us a result of... So this is still for equation 1. So both of these has I1 on it. So we'll have 8D plus 16 I1 minus 16 I2 equal to dVt. So we're done with the first one. Let's take a look at the second one. So I1 here is only negative 16 I1. Let me just verify that. Yep, it's only negative 16. So we'll have negative 16. I don't have to put the parentheses as this is only a single constant. Single I1, I'm sorry. Then this one has 3 I2. So when we factor out I2, so plus, so d squared plus 10d plus 16. Okay, I2 equal to 0. Now, I mentioned a while ago that this is a classic two equation, two unknowns problem. So we will be able now to solve I1 or I2 by doing the methods I mentioned. Okay. So for this time, I'll be using solution by elimination. We'll choose which we want to eliminate, either I1 and I2. So usually what we do is we choose the ones that has the smaller number of terms. In this case, I1 has 1, 2, 3 terms. I2 has 1, 2, 3, 4. So 4 terms. So we choose this one, we eliminate this one. So what do we do to eliminate it? Just a review. We actually multiply the first equation with the coefficient of the variable we're going to eliminate. So in this case, we are going to eliminate I1. So this is its coefficient. So we'll multiply the first equation with negative 16. And then the one at the bottom, we'll multiply it with the coefficient of I1 from the first term. Okay. So this negative 16 was multiplied here. Then we have 8d over 16 multiplied here. What would happen is that when we multiply this with this and this with this, it would give the same answer. Okay? So it's still negative 16 times 8d plus 16 and 8d plus 16 multiplied by negative 16. So why do we want this I1 to have the same coefficient? Such that we will be able to eliminate it by the use of subtraction. So we won't be showing the process of subtracting this. You should have known already that this is what elimination process is. So what would happen, and this would be eliminated. Well, we can do that, a bit of shortcut on that. So this one is eliminated, and this one would be eliminated. So the only thing that we have to do is to multiply 16 with the remaining coefficients here. So the first one, I have negative 16 times negative 16 I2 and negative 16 times dVt. Right? So I will multiply negative 16 first with negative 16. Okay? So negative 16 times negative 16, so 16 squared. Okay, just a moment. Oops. Where's my calculator here? View, show desktop icons, handy dandy calculator. Here we go. View, okay, so 16 squared. So we'll have 256. Yeah, it was supposed to be 256. I don't know why I did that. So this would be 256. So the 256 here is negative 16 times negative 16. So don't forget I2 equal to negative 16 dVt. So we multiplied negative 16 with dVt as well. Next up, we have 8d plus 16, and we multiplied it with this one here. Yeah, we did. So that will be 8d plus 16 multiplied by the d squared plus 10d plus 16 I2. So this would be a bit long. Let me just go ahead and check what we needs to be done. So we multiply it. We multiply 8d first. Anyway, this one is fine already. This is already our first equation. Let's just mark this up as equation 1. Let's just do a bit of computation for the first one. 8d times d squared is 8d cubed. 8d plus 10d would be 80d squared. 8d times 16 would be 124 or 128. Yep, 128d. So what I just did there is I multiplied 8d by this, and I get this, right? Next, I'll multiply 16 with everything here. So I'll have plus 16d squared. I'm putting it at the bottom because we still have to add this eventually, so it would be convenient to do it at the bottom. Plus 16 times 10d would be 160d, and 16 times 16, as we've seen a while ago, is 256. Okay, we add them. This multiplied by 0 is still 0, so we won't have any problems with that. So we will now have 8d cubed. We're adding, by the way, 80d plus 16d. d squared would be 96d squared. This is a 6. Uh, 128 plus 160 would be 288. And then we have the 256 here. Okay. And then that would be all multiplied with I2. Let's not forget that. Okay. Equal to 0. So this would be our equation 2. This is the one that we're going to subtract. So this minus this, okay? Or we could have this minus this. It really doesn't matter actually. So let's take a look and see what we can do here. So we have the two equations now, so we can have this subtracted by this one or this subtracted by this. But I guess it'll be easier if this is the one at the top, then we subtract it with this one. So let me just rewrite this. So this is already here. So it has I2 all over here, so it has 256 I2. Then this has negative 16 dVt. So this is the one that I was mentioning. Well, supposedly, the product of multiplying this and this should have been here as well. But we already, or we should have known already that it would cancel out, so it would just be a waste of time to include them. Check any discussions of solution by elimination or process of elimination for two equations to unknown, so that you'll be able to see the whole process for this one. In any case, I'll be subtracting these two. Technically, I have to distribute this one, but for the sake of simplicity, as they both have the same variable, so this would be 256 minus 256. So this would be eliminated, not I2, that's just the 256 I2 here. And then 0 minus negative 16 would be positive 16 dVt. So right now I'll have 8d cubed. I am going to write this 96. Wait, let me put in the I2 already. So I2 plus 96d squared I2 plus 288d. I just brought down this tree as there are nothing that we can subtract it with, and IY2. Okay, this is the one that we can subtract. 256 minus 256 is 0, so it's not going to show up here anymore, and this would be positive already, 16 dVt. 0 minus negative would be positive from basic algebra. Okay, now what do we do next? We already have the I2s here, but we can still do something here. All of these has d as its variable, so we can actually factor out d, or we could divide both sides by d, as there's also a d on the other side. Okay? Well, if there's no d on the other side, then we might as well have not done this, but because there's a d over dt here, could have that eliminated. So this would become 8d squared I2 96d. So what I'm doing is I'm dividing each term by d. So 288 I2 equal to 16 v of t. Okay. And then technically this is already the answer for the equation for I2, or the differential equation for I2, but we still have to bring d back to its original form, d over dt. Remember that we put in that d is equal to d over dt, so we have to go back. So this would become 8 d squared I2. This is the first term right here, over dt squared, plus we have 96 d. Where is the I2 here? There was supposed to be an I2 here, sorry. 6d I2 over dt plus 288 I2. equal to 16 v of t. So this is already the answer. This is the differential equation for I2. So the next step would be involving getting I1 instead. Okay? So we're done with the half of it. Let's go to I1 later on. Now, let us apply our fourth step to our second example. So we have to group I1 and their coefficients together for both the first and second equation, as with I2. So for number 1, so let me just write here step 4. For the first one, we have 1, 2, 3 I1s. Okay? So let me just put that in. So we have di1. Okay? We had 4 I1 plus 6 I1 here, so this should have been 10 I1. Let's factor out I1 here. So 1, 2, 3, have that covered? Nice, yes. Then we have here I2. Both of them are negative. If we take out the negative, well, it's up to you. We can take out the negative, or we can put in plus here and then negative 6 minus d. But it'll be better if you just put in minus here and have both as positive. So I'm taking negative 1 and negative 1 and I2 as a factor. Negative d, so this would become dn plus 6 I2 equal to v of t. So that would be my first equation here, which I already wrote in black ink a while ago. This would be our equation 2, same thing. I have one I1, no, I have 2 I1s here. I could put in the negative 1 here. So negative d plus 6 I1. Okay. Then the I2, so this would be 10 I2 plus d squared. So I will have here plus d squared, then plus 6d I2. So I cannot add this together pala. I'm sorry. So plus 6d I2. No, I shouldn't have written I2 here. So plus 6d plus 4 I2 equal to 0. Okay? Let me check that. So d squared 6d 4. 1, 2, 3. Okay, good. So I1 has 1, 2, 3, 4 equations. This has 1, 2, 3, 4, 5. So we'll just use this to eliminate. So we'll eliminate I1, just like what we did with the first example. So we multiply this one, this whole lot here, with this negative d plus 6, or if you want, negative d minus 6. I just distributed the negative d here. I1. Okay. Yeah. And this by d plus 10. That would essentially eliminate, oops, negative d minus 6. That would eliminate this and this, and we subtract it. So it's just a matter of multiplying this with this. Okay. So for the first one, well, this is basically the same, negative d minus 6 and negative d minus 6. Okay. So that would be, distribute this would be d squared. Okay. What I'm doing is putting this back as negative d minus 6 as well, and then just multiplying it. Then we have plus 36 here. And we just have minus 12d in the middle. Yeah. Multiplied by I2. Again, to make it clear, I just distributed negative d plus 6, negative 1. So this would be minus d minus 6. So it became minus d minus 6 here. And this one I distributed as well. That's why I multiplied negative d minus 6 to negative d minus 6, which is a square. So that would be d squared plus 36 and negative 12d. I2, okay, which is equal to, I have to multiply this as well. So negative dvt minus 6 vt. Okay. Next, let's multiply this with this. This would be our equation 1 still. So d plus 10, d squared 6d plus 4. So d first, we have d to the 4th. No, d cubed plus 6d squared plus 4d. Then multiply the 10, 10d squared. Ten times 6d would be 60d. And then 10 times 4 is 40. Okay. Just like what we did with our example number 1, we add them. So we'll be getting d cubed plus 16d squared plus 61d plus 40, and this will be multiplied by I2 equal to 0. Then it will be time to subtract. I'll just subtract this, I guess. Let's see what's easier to subtract from. Subtract this. This has the larger coefficients. So I guess I'll just subtract this with this. Okay? So minus, I'll be writing here, d squared minus 12d plus 36 I2 negative dvt minus 6 v of t. So we'll be subtracting this now. So this would be d cubed. 16 minus 1d would be 15. D squared. 61 minus 12, negative 12 where? So this would be plus, so this would be 73. D. And 40 minus 36 is 4. Okay. I2, and this would be both positive, dvt plus 6vt. Okay. So we're now going to move d into d over dt again, and then distribute the I2, just like what we did with the other one. We don't have a common factor of d here, so we're not going to factor out d from this equation, as this last term here doesn't have a d on it. So again, we let d, capital D into d over d of t, and I'm going to distribute I2 at the bottom here. So we'll have d cube I2 divided by d of t cube plus 15d squared, so that would be 15. That would be a numerical coefficient, so I'll put it here. 15 d squared I2 over dt squared plus 73d, so 73 d, let me just rewrite this, di2 over dt. Okay. And we have 4i2 equal to this would be d of v of t over dt plus 6vt. So this would now be our answer for the differential equation for I2. You only have to find the one for I1. So we'll move on to our first example. Try to find I1, or the differential equation for I1. We're now going to our last step, step number 5, in which we will be looking into the value of, or the differential equation of I1. So we'll be repeating the steps here, but instead of eliminating I1, we'll be eliminating I2, and then we'll be able to get the solution or differential equation for I1. So we will rewrite this, unfortunately. So we have here 8d plus 16. Remove this. So 8d (16) I1. Then we have negative 16 I2, or minus 16 I2 dvt. Equals dvt. Then we'll have negative 16 I1 plus d squared plus 10d plus 16 times I2. Equal to 0. So this time around, I'll be multiplying the bottom with the coefficient of I2, and then the top equation with the coefficient of I2 at the bottom. Just like what we did with step 4, but instead of eliminating I1, we'll be eliminating I2. So this would be d squared plus 10d plus 16. And then the one at the bottom here is negative 16. This would efficiently remove this and this. You just have to multiply. So we'll get our new equations without I2 and with only I1 remaining. So this one would be, it's right here, so 8d cubed. D squared times 16 is, I'll just multiply it here, 80d squared. So 80 cubed, 80d squared, and then 128d. Nice. 16 would be 16d squared. Uh, 160d. Then 256. So add 8d cubed plus 96d squared plus 228d plus 256. There we go. 8d cubed plus 96d squared plus 228d plus 256 equal to this one, no? What did I do? Oh, equal to GVT. Still have to multiply this with this though. So this would be d cubed v of t. Again, I am multiplying dvt with d squared, then dvt times 10d. That would be 10 dv squared, or d squared v of t, and 16 dvt. It's a bit long, fortunately. So this would be the new first equation. Let's not forget the I1 here. There's an I1. Okay. Then we have this one, negative 16, so that would be 256. I1, and this would be 0. So we'll subtract this. That caused the elimination of the I2. This would, 256 minus 256 would be gone as well. And everything will be brought down. And that is all not always the case. So this was just due to the problem being like that. Okay, you might be assuming that it's always like that. No, it just so happens that it was eliminated and everything else is brought down. So we'll now have 8d cubed plus, let me write the I1 already. 8d cubed I1 plus 96 d squared I1 plus 228 d I1 equal to dq v of t plus 10 d squared v of t plus 16 dvt. All of them have d as a coefficient, so we can divide all of them by d. So we'll eliminate d here, divide this with d, and divide this with d as well. Again, this was only possible because all the terms have a factor of d. So this is d, and this is d as well. So let's eliminate. So this would become 8d squared I1 plus 96d plus 228. Let me put the I1 here. 228 I1 equal to d squared. I divided that by d. The d cubed becomes d squared. Then we have plus 10 d vt plus 16 vt. And now we will now bring back the let d equal to d over dt as our ultimate final step. So this would become 8 d squared I1 over dt plus 96 d squared, oh no, just d, di1 over dt, no d's here, 228 I1. We have the d squared here, so this would become d squared v of t over dt. Nope, I don't need this. We just rewrite that. Plus 10 dvt or dv of t over dt. This is 10. Plus 16 VFT. And that's it. Well, that was a long one. So this would now be our equation or differential equation for I1. Okay, so we had this as our first, and this is our second equation, or second answer rather. Let me just box that up. Apologies, as if it was flying. Oops, I opened MS Word by mistake. Let me close that. And here we go. So that was the last step. Let's try to apply the last step to our second example and let's see what we get. So let's now move to finalizing our answer for our second example and doing the fifth step. So just like what we did with the first example, we will now be eliminating I2 instead of I1. So we will rewrite the equation again. So we have, just zoom this a bit, d plus 10 I1. Erase it, and we need space here. So let's now copy it from the one here. D plus 10 I1 minus d plus 6 I2 equal to v of d. And then, what's the other one? Yeah, this is the one let me just fix this. Let me make this plus and then this minus. I tried to simplify it, but I ended up making it go back to its original form, so that was actually a waste of time. Negative d minus 6i1 plus d squared plus 6d. D squared plus 6d plus 4 I2 equal to 0. So we will be multiplying it, both the bottom and the top, with the equations for I2. That's what we did with the first example. So equation 1 will be multiplied by this. So d squared plus 6d plus 4, and then negative d minus 6, okay. And that would eliminate our I2. Let's multiply this with this one and this one. So we have d squared and d plus 10. So let's just multiply d first to d squared. So we'll have d cubed plus 6d squared plus 4d. Next, we'll multiply 10 with this equation. So we'll have 60d. Oh, no, that's 60d. 10 times d squared is just 10d squared. So 10d squared, and then we have 60d, and then we have 40. We add those up. We get d cubed plus 16 d squared plus 64d plus 40. Okay. And that is the one multiplied by I1. But we're not done yet. We still have to multiply VT with this one. So that would be d squared VT plus 6d VT plus 4 VT. And there we have it. This will be our first equation. And then we multiply this 2. We'll get d squared. I'll just put it here. We did this a while ago. Let's subtract it. So this would be d squared. Negative 16 times negative 16 is 36. Okay. Negative d times negative 6, then times 2 would be negative 12d. Okay. We subtract. We will have d cubed. 16 minus 1 would be 15. I'll distribute I1 as well. 64 minus negative 12, so that would be plus 12. So that would be plus 76d. 40 minus 36 is 4. And then we'll bring this whole lot down. D squared Vt 6d v of t plus 4v of t. Now question, can we do you call this divide both sides by d? In the first example, we were able to do that as all terms have a coefficient of d. Unfortunately for this one, or the second example, if we take a look, these three terms has d on it, but the last one doesn't have a d, and this one lacks d as well at the last term. So if at least one term doesn't have that single coefficient, we won't be able to do that. So we stay it as is. Then that will be the time that we insert or we put d into d over dt already. Okay. So we have this. So this would be d cubed I1 over dt cubed. I'm talking about this one. Next, 15d squared I1 would become plus 15 d squared I1 over dt squared. And how about 76d? It becomes 76. This has to be had I1 here, sorry. 76 di1 over dt plus 4 equal to d squared vt. So I'll have d squared vt here. I'll let d over dt as our example. So this would become d squared v of t over dt squared. 6 dvt, so we have 6d here, so plus 6 capital D change to small d v of t over dt, and then finally we have plus 4 v of t. So there you have it. This would now be our differential equation for I1. This would be the model rather, no? For our I1. Just backs this up. Okay. So it is a bit tedious, especially if you are allergic to differential equations. Now, the tediousness of this solution, will make you appreciate doing this by Laplace transform, because Laplace transform will be able to algebraically use the counterparts of each components, okay, and get the answer or the differential equation a bit faster and simpler. Anyway, guys, that's it. Thank you very much for listening, and hopefully we were able to impart to you some knowledge about modeling using differential equations for electrical systems. I do apologize for the handwriting as I am using a mouse. And if you like this, please subscribe and like the video and leave some comment if you want. If you have any further questions, just leave it in the comment or direct message me. Okay? Thank you very much, and I hope you have a great day.